Okay, hang on a sec. Anyway, I'll walk around. This camera and lighting is a bit in the way. This is a Stirling engine, designed and built. Gosh, on about 18 years ago. I did a video of it some while after that. It was one of my earliest videos, and I didn't say a word. I just was practicing, playing around with the camera and everything. It turned out okay. Demonstrated this running, but it'd be better to get a little bit in detail of what I did, why, how, I just showed the thing off a little bit. I am proud of it because it works so well. I did not have specific plans for this. It was just kind of by the ear. I'd seen what others had done. It shows. At that point, I did not look on the internet to get advice. There wasn't so much YouTube or anything. But I go to Steam shows and things like that. And there's hobbyists there that often have the Stirling engines, their own versions of them. That was really cool. So I decided I won't build one, and so I did. And this is it. I thought I'd just run the thing and then do a teardown. Well, I think this thing's dirty. It's been sitting down in my dungeon for years unattended, and spiders and beetles and dust and smoke and wood smoke, and everything is it's kind of gummed it up a little. No, it would probably, I'm sure it would run if I just put some fuel in and added some water and gave her a spin. She'd run. But it needs a good cleaning, so I thought, well, why not do a teardown of it first, then do the cleaning. I'll videotape the teardown and explain what's what and how and why I did it. And then I'll clean it. I'll describe what I do, but I'm not going to video it. That's just a waste of time. And then once we get it all cleaned up and set, we'll run it and demonstrate what she does. So, let's see. Really, to get this apart, you really only need one tool, and maybe not even that. Well, I'll start with some of the components here. What's what? Well, source of heat. That's this. This is a hobo stove made out of a couple of aluminum cans. There's plenty of information online. YouTube, check it out. Look up penny stove, hobo stove, and there are a lot of different variations of this. These work very well. I have used these camping, and man, they put out some heat with a minimal amount of fuel. The fuel here is denatured alcohol that I use, which, by the way, is the solvent I'll be using to clean components. But anyway, just a simple homemade alcohol stove works very, very well. I'll get into some detail on that, I guess, later, maybe, time given. And that sits where it was here and heats this end of this can. This end of the can is the cold side, hot side, cold side. And there are a number of ways of cooling the cold side. You could put heat sink fins on it, maybe have a blower blowing air across it. You could solder on a tank and fill it with water and just use that. I've seen some pretty nifty schemes from guys that actually have a tiny little radiator and a little pump that the engine turns and pumps water through the water jacket, and then through a little radiator. Very, very cool ideas out there. Me, I'm cheap and dirty. I just got a piece of cotton strip here. This is just, nothing special. This is a piece cut off of a mover's blanket. But it's 100% cotton fiber, rough cut, very water absorbent, and that's why I chose to use this particular thing. This can, obviously cold side, hot side, you can see the discoloration from the heat here. And there's a little bit of rust. This thing, like I said, it's 18 years old. This is the original can that I first used, just a soup can. Actually, I think that had chili in it. This can's held to this mounting, this block. This is all aluminum. The can, of course, is steel, and it's held on with a single guide rod. Little nut, a washer, like that. There's also a Teflon washer there to help seal. It's not imperative that this be tightly sealed, but I had the Teflon washer, so I used it. And there it is. That's just a regular steel washer, stainless. Stainless 440. I would have preferred to use 632 for this, but it just wasn't to be. This is made of junk. It's scrap material, all of it. I'll set these aside. You can see the stud sticking out of there. That's actually a guide rod. This rod is threaded just like this on the other end of it, and that is threaded into this aluminum block here. Now, let's see, pull this off. You can see what's in there. It's nothing but an empty can. The displacer and guide rod, and the displacer push rod. This, again, it's a piece of a can like this. I don't remember exactly what. It was just a soup can of some sort. I cut out the middle section of it, which on that can had these ridges, these ribs, corrugations, all the way through the middle of the can. These corrugations are there to add stiffness, and so you just don't want a flat metal there. You dent this just picking it up. So I cut both ends of this can off and cut two sheet metal aluminum discs, one for each end, and those are something like a 32nd of an inch thick or so. I forget the gauge. And those were each just silicone rubbered adhesive into each end of this what was left of the can, the center part of the can. I should have used high temperature silicone rubber. Ideally, I would have, the red stuff, look rust colored, like the color of this gasket. But I didn't have any handy. Well, I had some handy, but it was too old and it didn't cure, so I just went ahead and used white stuff. It's working. It's never given a trouble, so use what you got. It may not be obvious, in fact I'm sure it isn't, but there, well, let's see, I'm going to move this around a little bit. You can see how that operates, like that. Another view here. There's the guide rod. This rod is this piece here. Notice this kind of flops around. That's intentional because it allows you to adjust the clearances and the gaps and the centering of this very, very easily just by moving this around and then tightening the nut. So there's the guide rod. Obviously that's going through the center of this. Now inside of this let me get rid of this gasket. Well, maybe just let it flop there. There's this is a solid, this rod here is solid steel, and it is, I believe, nickel plated. A very smooth surface. Inside of this can, which you can't see, this rod, this guide rod, passes through a piece of metal tubing. Very thin-walled brass tubing. You can get at any hobby store. Or, if you get one of these telescoping antennas, you got everything you need. You pick the size that this rod will fit through, not tightly, but closely. Well, there's maybe 3/1000ths gap. The difference between the diameter of this guide rod and the inside diameter of whatever piece of brass tubing. These antenna sections, they are made of brass, I believe nickel plated. Very handy for bits of concentrically sized brass tubing. Hollow, very lightweight, and pretty rigid. An excellent choice for this kind of work. And once you may be able to solder to it, depending on what the plating is. If you need to solder to it, you can just get some emery cloth and burn off the plating, and you can solder right to it readily. This here, geez, I hope you can see this. This piece here is a push rod, and that's obviously it's connected to an armature, and that's purpose it clearly should be is to just move this displacer back and forth inside the outside can. You could call that a piston, but it's not sealed to the cylinder of the can. There is a space between. There must be. The reason being that this just pushes the gas, air in this case, inside that cylinder from the hot side to the cold side, the hot side to the cold side, and so the gas air must pass by this. I don't know if it matters about these corrugations here, about the airflow. Probably does in some subtle way. It might help. It might be a hindrance. I don't know. There's a number of schools of thought on that in my head. I'll leave that alone for now. And by the by, one of the mistakes I made, actually, I think the mistake I made when I first built this, I put it all together just as you see, and it ran, and I was quite happy with it. And as it was running, something went bang. Uh-oh! Didn't see nothing broken, and then I took the cylinder can off, and it had blown out one of these end caps. The reason is this inside was sealed, and as the gas inside of here, air, heated up, it expanded, of course, and the pressure built up inside this can. I didn't even think about that. Stupid. So the pressure built up, and it just blew one of these end caps clean off. Oops. So all it took to fix that, well, you probably will not be able to see it well, but there's a tiny little hole there. It's just a vent. So as the air in here heats up, it expands, it just comes out that little hole. Problem solved. Let's see. So that's a displacer. Pretty obviously that with the spinning just oscillates back and forth. The piston here. This is driven. This is the driver. This is what's, as the pressure in the cylinder increases because it's being heated and cooled. That causes this piston to move, which of course drives the flywheel, which drives the displacer. I'm not going to get into a whole lot of operational theory on Stirling engines. Good Lord, there's a bazillion descriptions available online. Some of them, and most of them much better than I could do here. Time constraints, you know. I'm more interested in just describing this particular engine, what I did, how I did it, why. The purpose for this brass tubing in here is to provide a nice long bearing surface on this guide rod. The same principle applies. Turn this around. Here, that's the push rod for the displacer right there. This again, this is a solid piece of solid steel, nickel-plated probably rod, and here is another piece of this stuff that this just fits nice, not tight, but very loosely. Close enough that it doesn't let a whole lot of gases move through there, but loose enough where there's very little friction. By the by, when you're doing this, if you're doing this, do not use oil on anything. Maybe up here on the motor, or the flywheel bearings, and so, but do not use it in the piston. Do not use it anywhere here. Graphite only. There are reasons why you don't use the oil. Number one, it's flammable. It could cause an explosion. If vapors of it accumulate in the cylinder, you don't want to use oil. The other thing is it's viscous, and where graphite lubrication is not viscous. Oil will slow this down. You see how freely this turns. It's taking very little effort to get this spinning, and it goes for quite a while. So the same type of bearing here as there is inside this displacer. Alright, so what's next? As I said, you don't need much in the way of tools to get this beast apart. At least to do a maintenance and cleaning and lubrication on it. Not difficult. These two bearings here, they are ball bearings. Those were liberated from a small, like a fish aquarium type air compressor pump, air pump. Just a little shaded pole motor, and I don't know if you can tell, but the centers of these are eccentric, and these went that way very little and drove a diaphragm. They were diaphragm pumps. But these bearings made very handy use for something like this, so that's what I did. Let's see, 1 second. Flex couplings. Obviously, this has got a flex. Yeah, there's a number of ways of going about that, but I just use really flexible silicone rubber tubing. This happens to be 1/8 inch inside diameter and a quarter inch OD. I used what fits. Happen to have some handy. But if you're going to use this method, leave a gap so it can flex. If you put it right up, it won't flex so well. Leave a gap so it does that. Doesn't do much in the way of compression and stretch, but it's plenty flexible this way, which is what you want. It's also forgiving in every direction, so if there's a misalignment this way or this way, who cares? This will manage it. Obviously, this is, you can see how bendy that is. Very much so. And so to get that off, there's a screw threaded into this, about which a piece of this tubing is attached. So it's just finger tight. So unscrew that, and that leaves the drive piston free. Get into that in a sec. These bearings See how freely that moves. Now, if you are, these are ball bearings, of course. If you're using ball bearings and it doesn't do that, you're going to have troubles. If bearings, typically they're packed with heavy grease, and you could stand this thing like that and let it go, and it'll just sit there, or maybe slowly. You don't want that. These happen to be lubricated with a very light oil. I guess because of the application they were in. They're not worn, if so, not very much, but they're quite loose. If you have bearings that are not quite loose, you can pick out the seal carefully, pick out the seal, hose it down with solvent, WD-40 maybe, get all the heavy grease out of it, and just leave the light oil. WD-40, it's probably all you need. And occasionally you might have to hose it out to get rid of dust and grime that might have got in, but that'll work for you. So there's that. Now this piston. Now here's the flex coupling. This piston, what is that? Where do you get this? Clearly the cylinder for this piston is just a piece of common copper tubing, copper pipe. And I happened to find an aluminum can that fits in there just nice. No, it provides a fairly good gas seal, but it's not tight. There's no rings on this. This moves very, very freely through here. And an aluminum copper interface with moving parts, well, that may not be the best thing, but they're both soft and forgiving. So that should probably last quite a while. Now, what is this? Where did I get that? Get a couple of spare stuff here. Maintenance kit. Here's an earlier version I made. Also fits in here, but it's a little tighter. The reason is this edge. When I cut this, I'll show you what these came from in a moment. But when I cut this component apart to get this can, I made a mistake. I did not leave this here. This, I don't know what to call it, but it's very effective at keeping this round where this is not. And somehow, just from handling or whatever, or maybe from cutting, it got a bit deformed. And so it's a little trickier to use this one. You see, it doesn't really want to fit in there. I'm not going to drive it in there. If I had to, if for some reason this utterly failed, I could make this work. But I'll keep it handy just in case. This here is a piece of that telescoping antenna rod. Just a hunk of it. It's hollow, nice and rigid, very lightweight, and it's just epoxied down into the bottom of this. Maybe the epoxy is probably about 1/4 of an inch deep from the bottom. This one I used RTV, silicone rubber. Gives it a little bit more flexibility, and it's less likely to be wrecked by the heat that may develop in here. And there's some warmth. It's not terrible, but and plus this is rigid. I thought it would be better to have this a bit flexible, and then that would augment the operation of this flex coupling here. So what is this? What is this? Oh, here's another can. It also fits in there. Little tight. This might have been better because it has more bearing surface, but it's a little dented up. And I did leave the, I guess chamfer, I guess is better, good word, on there to stiffen up this open end. And if I had to use this, I could probably, fix it enough to make it work, but I don't think I'm going to have to. We'll just keep it. Spare parts. There you go. There's a bag of them here. Here's the lubricant I used. The powdered graphite. The only thing to use on these. Let's see what else we got. Because it's kind of hidden here, I've got a spare crank. I use the crank the way I do. In other words, this one, the push rod for the displacer, that cams right off of a bolt through the flywheel. And then there's this piece here to which this bearing for the drive piston attaches. This allows me to change the phase of these two motions, and it also allows me to change the amount of the distance traveled by the drive piston. The distance traveled by the displacer is fixed, and that's going to have to do with the position of this fastener here to the flywheel. That pretty much goes from, almost all the way from one end to the other. To change that, I'd have to put more holes in it. I thought about doing that. That was an option, but I figured where I put the hole here, it got this close to where it wants to be. Leave a little bit of gap here, a little bit of gap here at the end. I just estimated it. So that's what this piece here looks like. That fully adjustable. And rather than getting stuck with a crank where you got to rebuild the whole, remake the whole thing to trim it. What else? Maybe just a bag of stuff here. Some spare fine thread machine bolt. Ooh, it's handy. Even got a Allen wrench to fit those in case I wanted to adjust it. I'm going to leave that set the way it is. This thing runs as it. I have not fine-tuned this thing. I just put it together the way it is now, with the phase, and it's kind of eyeballed it, and the daggone thing works so well. I'm not messing with it. I thought about it, but nah, that's not. It does what it's supposed to do without me messing with it. So leave that out. Don't need this. Pardon. Lay here, just trying to keep track of what I'm doing here. So yeah, the piston here, I didn't even get to it yet, is one of these. It's an aluminum capacitor, an electrolytic capacitor, the electronic part. Most of what I do involves this stuff, but it is a deep drawn aluminum can, and you just cut the end off of it and pull the guts out, which is aluminum and paper and some electrolyte chemical stuff, relatively harmless. And cut the wire off here, and there you've got your piston. And the outside diameter of this just happens to be perfect fit for this application here. Now this has shrink tubing over it, so it's not going to fit in, plus the wire. But with that wire cut off and this shrink tubing sleeving removed, this can will go in there. In fact, the piston I use, this one, is from one of these exact cans. This is what's in here, like that. Alright, so let's see what else before I forget. Oh yeah, this won't unscrew because this won't turn. So the only way to deal with that is to peel off this flex coupling here. You can see that's now cut loose. And if I want, I can unscrew this. In fact, I'll do that and clean everything up. Got that loose, got that loose. This flywheel, you see how easily that spins. Again, it's two ball bearings supporting the shaft. Grab the shaft. This is not bolted in. It's just a small friction fit. You can see the shaft. Those are the spider webs and hair and beetle juice and God knows what. And there's the flywheel bearing and spider eggs and the shaft, the hub attaches the shaft to this disc. These, by the way, are counterweights. It's 6 25-cent bits, quarter dollars, just taped on there as a counterweight to counter the operation of the motion of this mostly. It does help, and so it costs $1.50 for that counterweight. You get a better view of what goes on. There's the displacer cam, and there's the drive piston cam. And there you go. This. What is that? Well, what special hardware store do you go to get that? No, you don't. No, you can, but you don't make. Because you make your own. Let's see it. What's the best view? Probably move stuff out. I guess you could probably see that okay. Now these two end bells here. This is just a solid hunk of aluminum with a hole drilled through it and tapped holes for these mounting screws. What these came from is one of these, a stepper motor. This, see, these two pieces are these two pieces with the core removed and no armature, obviously. Don't remember where I got a shaft that exactly fit these bearings. They probably came from another motor. I scrap a lot of the stuff, or have anyway. Now this came out. I used to work in R&D, and this was part of a prototype. This is a stepper motor driver module, and the motor it was driving. Nothing special about it, but that's what these are. Excuse me. So keep that in mind. There are a lot of sources of bearings and things like that. Even if these are ball bearings, but they don't have to be. You could use something from end bells from a small motor that use sleeve bearings. It doesn't matter, as long as they're very, very loose bearings. Meaning very low friction bearings. You don't want them sloppy loose. I don't mean that. But very, very low friction. Now this has permanent magnets in it, so you spin this, it breaks itself because of that. But you remove the magnets and this iron core with the windings and everything, and you're just left with these two end bells with the ball bearings in them and a shaft that you can use. You're golden, and they work very well for stuff like this. Used them on other projects. So let's see, is there anything? Well, I'm going to pull this anyway. This copper tubing, it's a nylon 1/4 20 screw, and that just kind of clamps this in there. And there's a gasket. The reason for this gasket, long story. I had intended this hole to be sort of a honeymoon fit and just press the copper in there. But I thought better of it in case I wanted to play around with the diameter and length of this. I wanted to be able to easily swap it out. So I cut this hole large enough to accommodate this piece of red rubber gasket. It just wraps around there. A little tricky getting it in there. You have to use a little spit shine on it to get it to slide in, and just give this a twist just to keep this from moving around. Um, this is nylon, so it cannot damage this or bend it, distort it in any way, and nor will it chew through the gasket here. So all of this, it needs to be cleaned. Basically, I'm going to use the isopropyl, denatured alcohol. This stuff. This is what I use for fuel, and it's a very good solvent for removing grease and oils and smoky and dust and spider shit from the moving parts. And then I'll apply graphite to these sleeve bearings here and here. Graphite in here also. Put it back together and do a demo. I'm not going to bore you with cleaning and wiping. It's I know it's boring. So I'll be right back. Okay, got her all put back together, cleaned and properly lubricated. There's a graphite here and there. I did a test run on it. I did film it or video it. But I was using a strobe tech to measure the RPM, speed. And the video is about useless because of that. And so I thought better of it. I already measured it. It was turning. In that first test, after about a minute of running or so, it was 540 RPM. So you give you an idea what this thing's turning. But I've got subdued lighting here for a reason. Just wanted to demonstrate a little bit about the behavior of this stove. Let's see. I've got some denatured alcohol here. About 30 milliliters. I'm going to put about 10 in. About 10 milliliters in there. And that's going to go for a while. It's sitting here on this, the base platform of the engine here. That's safe enough. It's not going to overheat anything here. Well, I maybe move it over this way a little bit. And good Lord knows, I better check. I apologize. Yeah, we'll center that a little bit more. Better. Pardon me. And I'm going to light this. Now, at first it's going to just burn from this center. And once this stove heats up, it's going to begin to vaporize around the outside. There's a space between the inside where the fuel is and the outside. And it will begin to jet alcohol vapor out of these holes around here. And boy, I'll tell you, man, these get hot. But just to illustrate just the behavior of these, for an engine of this sort with this size cylinder, this is about perfect. And there are a million ways, well, maybe not a million, but there's a bunch of ways to make this much more efficient. I've got so many projects in the hopper, I don't know if I'll get to it. But yeah, to put a water jacket on would be optimal. This me using just this soaked piece of cotton does the trick. But yeah, this is starting to cook now. You may be able to see it jetting out of those holes. And I was hoping with the reduced lighting that these flames would show up. This denatured alcohol doesn't put out a whole lot of yellow. And what little bit you're seeing there is impurities and dust and stuff in there. But boy, yeah, that does give off some BTUs. let's see, that was, yeah, about 10 milliliters of alcohol. And that'll go like that for probably 4 minutes, 5. I'm going to cut this and just let that go out, and then the next thing is, we're just going to run the engine. I don't want to waste too much time with this, but just to give you an idea of what I'm using to fire this beast up. See it? Okay, got it all ready to run. I've already run it since I put it back together. Do adjustments, alignments, this can, and so forth. Yeah, but rather not to bore you with that. It's not exciting. Well, she's going just fine. I also did I checked the RPM on it after about, I guess a minute or so of running. She got up to 540 RPM, and it don't sound like a lot, but for something with this mass flying back and forth, that's not shabby by my reckoning. So I got some water here. I'm just gonna pour it on this cooler, this cotton thing here. It's gonna spill all over the place. That's fine. This is all soaked. This sheet here is soaked. Fire safety. As this stove is sitting on top of a soaked, folded up paper towel. Just in case something spills, who cares? It just goes out rather than makes me unhappy. Now I just soak this cooler real good, and what do we got? About 30 milliliters of denatured alcohol here. I'm gonna, let's see, how much are we gonna put in there? Oh yeah. Let's go ahead and put 20 in. Okay, so that's about 20 milliliters of fuel. Fired up. Oh, probably won't be able to see the flame so much with this bright lighting here. I'm going to position this so that once this thing starts jetting, it will sort of more or less evenly lick up around the sides and up the back of this. Shouldn't take but a moment for that to get hot enough for this to actually be startable. And there it is. And that hasn't started to jet yet. And once it does, it will take off. Goes through a resonance. Gets past it. Be very quiet. These tend to be. Coming along pretty good. I don't know if the camera picks this up, but with this light, you can see back here, refraction from the heat of this. This very slightly warm to the touch. It's cold. This is warm. That is hot. I'm not putting fingers on that. But this is warm. Let's see. Pardon me. I'll dump some cold water on it. See if it does anything. Yeah. Might have picked up speed a little bit. But ideally, a water jacket around this would be the thing to do. And, oh no, maybe I will. How long would it take to take a can and solder up the... I don't know, probably not showing up much yet here in the camera, but it's there's steam coming up from this. Not unusual. I'm going to get my hair tangled in that. Lovely. Then it'll pretty much go like that until it either runs out of fuel or this dries out and overheats, and then it will just quit working. But yeah, a water jacket around here. That would not be difficult to fashion. A little bit of soldering skills, it wouldn't be difficult. Or fuel's running out. And I'll just let her go. There's that resonance. Chicka, chicka, chicka. There it is. And through it. Past it. And there you go. And this is completely out. And by the by, this just finished burning, and I can handle it. It's a little hot, but there's so little mass to these things that, you know, it's done. This you may be able to see is steaming. And as usual, the can has come loose, you know, tighten up on the nut after a run. And, yeah, geez, that is hot too. And of course, all of that heat from here was being put to here, being pumped there. And you may be able to see steam coming from this. And, just lay that on there. Let that cool off, dry some. But there she is. Hope this inspires somebody to make this or something like it. Ain't really that difficult. Hope this helps. See ya.